Hello, welcome to Science Chomp. Today we're going to be looking at relative age dating. Now, as you can see from the computer screen, I'm going to be working straight off my PowerPoint, and it gives you a little definition of what relative age dating is. Now, in simple terms, whenever you use the word relative, you're always comparing one thing with another thing. So, for instance, the relative age of your father compared to yourself is that he is older. This isn't like a numerical value, it's just a comparison between his age and your age. So relative age, in particular, in this case it's the relative age of rocks, is basically the age of a rock compared to another rock. And so it's either going to be older or younger. Here we have the principles of relative age dating. Now, these allow us to figure out how old a rock is in comparison to another rock. So the first principle is superposition, and this is effectively saying that the rock layers at the bottom are older than the rock layers at the top. So youngest at the top, oldest at the bottom. And the idea is that when sediments are deposited, like for example in the ocean, as it hits the bottom, it effectively gets compacted and turns into rock. And then the next layer that goes on top obviously is going to be younger than the layer beneath it. And that's how you use the idea of superposition. The next one is original horizontality. And this is saying that originally the layers were deposited one on top of the other horizontally, but then geologic events can occur which could cause this kind of tilting, but the idea is still that originally the whole thing was horizontal. And finally we've got lateral continuity. Now, lateral continuity is when you have sediments that get deposited and it spreads out evenly in all directions. And because it's in all directions, you call it lateral. Lateral literally just means side to side, but it just spreads out all over the place. Here I'm demonstrating lateral continuity. So I've deposited some sediment on a plate, and because the sediment is limited in amount, it's not going to cover the whole plate, no matter how much you spread out. So what's happening is the sediment gets spread evenly as far as it can, but then obviously when you run out of sediment, that's it, you run out of, you come to a halt. You can also come to a halt if you come across a barrier. So this ketchup sachet is acting as a barrier, and clearly it's not going to pass through that barrier. And if you want to know the definitions of superposition, original horizontality, and lateral continuity, pause the video now and just have a quick read. Hopefully it all makes sense. Another thing to consider when looking at relative age dating is inclusions and cross-cutting relationships. So let's have a look at what all of these mean. So here, these are your sedimentary rocks. These ones are the oldest, they were deposited first, and the layer up here, this is the youngest. Now here what we have is something called a dike. So a dike is when magma intrudes through the rock layers, and obviously to cut across all of these layers, it actually is younger than all of these layers. So you've got the oldest rock down here, and then gradually getting younger. This one's really young. And then this one is the youngest of them all. So anything which cuts across layers of rock is younger than the layers of rock that it cuts across. However, one thing that it might do, as the magma is going through the rock layers, it might bring up bits of rock from down here above. These are what you would call inclusions. And inclusions would be older bits of rock. So if it dragged this bit of rock all the way up here, even though it's all the way up here, this bit of rock is older than the surrounding rock. Okay, in fact, it's older than the rock even from down here. So that's something to consider if you are aging rocks. We've got another cross-cutting relationship over here, and this is a fault. And as you can see, it cuts across these layers of rock and also the dike as well, which means that this is younger than the dike. So in order of age, you've got the oldest down here, then it goes up and up and up. So younger, 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 younger. This is younger still, and this fault line is the youngest of them all. So here we are summarizing inclusions with a nice little definition, a piece of an older rock that becomes part of a newer rock, and that they are older than the rock that surrounds it. So here we've got the summary of cross-cutting relationships. Any feature that cuts across a rock or layer of sediment is younger than the rock or layer it cuts. So here we've got a nice little diagram, and here's a picture in real life. This is an interesting picture. So this is, I think this is captured in Egypt. I'm not entirely sure. It's one of these Middle Eastern countries. We've got a dike here. So this was magma, and obviously it cooled down. And you've got a fault that runs across through it. Okay, next up we've got unconformities. And what an unconformity is when you have a rock like this, and what happens is it gets weathered and eroded away, and then you get new rock being put on top. Okay, so you've got three different types of unconformity. You've got disconformity. So this is when you have sedimentary rock and a bit of it gets eroded away. Now, when you have erosion, what's effectively happening is it's chipping away at the rock. Now, if you're aging rocks based on how deep they are, and you're chipping away at the top layer, and then new rock gets put on top, what that's going to give you is a gap in the rock record. Or you can think of it almost as a gap in time, as in the history of the rock. So anyway, as I was saying, there's three types. There's disconformity, and that's where sedimentary rock gets worn away, and then new sedimentary rock gets put on top. So that's called a disconformity. An angular unconformity is when you've got sedimentary rock which is sort of at an angle, and it's going to be at an angle because, you know, tectonic geologic events cause the ground to kind of shift and tilt. So it's at an angle, and then you have erosion occurring, and then new rock being put on top. Again, both sedimentary. So that's angular unconformity. And then finally, you've got non-conformity, which is very similar to disconformity, except you've got igneous rock or metamorphic rock, and then that gets eroded away, and then you get sedimentary rock placed on top of that. So these are unconformities. Let me show you this page. This page has the definition of unconformity, so maybe you want to pause it, have a quick read through, and I'll just explain it again. So it's when a rock which is deposited down gets eroded away, so the top layer is eroded, and then new rock gets placed on top of that. And because that layer got eroded away, that is basically producing a break or gap in the rock record. So unconformities leads us to correlation. So how does it all link up? Well, an unconformity gives us a rock record that's incomplete. And to fill in these gaps, what geologists do is they match rocks in one location with rock layers in another location. And matching up these rocks is called correlation. So how does this work? Well, we've got this thing. So have a look at this picture. Here we've got a basin, and you got deposition happening. Now you have to understand the ground was already sort of shaped like this, so all of this layer, this is all the same age, right? That layer, this is all the same age, and you can see you got like lateral continuity going on here, because this layer here, this stops, okay, because it runs out of material. And then you got that layer, this layer. So all of these layers, which are the same color, these are the same age. Now, if you take cross sections of the different parts, you can actually figure out which bit of the rock is how old relative to other parts of the rock. So for example, here you can see that this thing called David sandstone, you get it here, here, and here, and all of these bits of rock are the same age based upon this. So that's called correlation. So again, if you want to have a read of this, just pause it. It's effectively matching rocks and fossils from separate locations. This is called correlation. So I mentioned fossils, so let's talk about index fossils. So this is an example of an index fossil. This is a trilobite. And if you want to have a quick read, just pause the video now and just have a read through. Anyway, let's talk about it. So the meat of what you want to know is right at the very bottom. So index fossils are basically species that lived on Earth for a very short amount of time, but they were huge in number and they're literally everywhere. So they're the things that you need: short length of time, abundant, which means high in number, and inhabited many locations. And because of this, if you find this particular fossil in a particular rock, we know, well, this rock is that old. Okay, so let's have a look at what all of this means. Okay, here we have basically like a index fossil here and over here. Okay, so we know that this rock and this rock have got to be the same age. Similarly, we've got these shells here, so we know that this rock and that rock is the same age. So this is why index fossils are useful. Okay, and that's about it for relative age dating. So just to summarize, it's basically using different ideas to tell us how old rocks are in comparison to other rocks. Okay, thank you very much for watching, and I'll see you in the next video. Goodbye. And this is how they do like this in the movies. They just distribute their washing up powder like this for whatever reason. Don't know why they can't just buy it from the supermarket, but they use usually a card, and they do like that, and then they just split it up. You know, it's obviously a very valuable commodity. You want clean shirts after all.